So some metric then beyond accuracy. Let's say I have a classifier. Yes, Manoj.
Sorry, I have this question. This is more related to my research, but I think I can benefit here. If we have a very a highly imbalanced data set, so do
Mhm.
we have preferences in terms of handling those imbalances with the loss function? Like, is there some loss functions that are made for that kind of setup?
Mhm. What do you think yourself?
Well, with my research, I know that there are some Tversky loss and dice loss, which
Mhm.
helps in this kind of thing. But if there's like I heard you talk about a combination, and I haven't really explored those. But if there is a
Okay,
definition, I should look.
that's a very good question and also a very good segue into this section. So I think you'll get your answer within the next 5 minutes.
Okay,
Just bear
sure.
with me on these slides.
Yeah, sure.
Okay, so let's consider this classifier here. It's going to be classifying, in this case, it seems like it's classifying dog versus no dog. In blue, the ones that are outlined in blue are predictions of the model as a dog. Of course, there are cases where the prediction is incorrect, like this wolf over here. And there are cases where there are probably other dogs that it hasn't classified positive, right? So if we were to call those true positives and false positives and false negatives, you can see that the ones outlined on this slide correspond to these three different types of errors. Now, what we want to now define is a few different metrics for evaluating performance of classifiers that kind of dissect the accuracy maybe a bit more granularly for our task. The first one is called recall. And the recall intuitively is the fraction of positively labeled instances, go through that word by word, positively labeled instances that are predicted as positive. So the fraction of positively labeled instances, that means all of the instances in the denominator are positively labeled, and some fraction of them we're going to be actually predicting as positive. Complementary to this, we have something called precision, which is now, before we had positively labeled, and now we have the fraction of positively predicted instances that are labeled as positive. So now it's a bit different in the denominator, and the numerator is still the same. This is what we call precision and recall. And you might be wondering, is there a way to optimize for both of these at the same time? What do we call that? Does anyone know?
F1 score.
Right. So the F1 score, if you've heard of it, is called is the harmonic mean of precision and recall. Harmonic mean just means that take the product and divide by the sum in this case. Multiply by 2. Now, to maybe help just build a bit of intuition, we can see here that the numerator and denominator contain the same terms. And we know that the values of false negative and false positive are positive integer values. So the domain of both recall and precision is between 0 and 1. What is the domain of F1 score? So this is between 0 and 1, and that is between 0 and 1. Then the sum of them is between 0 and 2. Right? If this is between 0 and 1, and that is between 0 and 1, then the product of them is between also 0 and 1. We have a 2 in front of it, so 2 times a range of a domain of 0 to 1 divided by another domain of 0 to 1 is also 0 to 1. Yes, Jim.
Okay, consider the case that, okay, both the nominator and denominator are between 0 and 2, as you say, and the denominator is bigger than
Sure.
denominator.
And so you might have something that's smaller. I think in the case of, you're absolutely right. If I had, x times y divided by a times b, then what Shima is saying is that could turn out to be like 1.5 divided by 0.5, which is equal to 3, and that's a number that's not in this range. But because we have precision and recall, then the denominator and numerator are tied together in a way. So the value of F1 score won't be larger than 1. Yes, Shima, no Shima.
Yes.
Maybe I'm wrong, so push
Yes,
back.
F score is only a comparative measure, and
Okay.
we can't say that it is 1, so that the method is good, or it is not 1, so the method just in comparing two methods, the F score would be a good measure.
Okay. So you're saying that it doesn't fall between 0 and 1? Is that what you're saying?
Yes. Yes. And unfortunately, I think, and I saw it in some works. Maybe I'm wrong, but
Okay.
F score could be more than 1 sometimes. Maybe because of the.
Well, that's a good point, and maybe I'm wrong. So I'm going to assign a homework to the class as well as myself. For next lecture, let's try to think about a case where the F1 score would not fall between 0 and 1. Just think about two numbers, right? There's only P and there's only R that goes into this, right? Come up with two numbers that this would not be between 0 and 1. It would certainly be larger than 0 because all the values are positive. So we don't expect anything to be smaller than 0, right? But someone come up with a case where this is larger than 1, and I will retract this statement. I could be wrong.
So precision and recall are still between 0 and 1, right?
Yes.
So we can just try the extremal cases and see that F1 score cannot be beyond 1. It's very clear from that.
Okay.
I mean, that's one of the ways I can
assuming that this is a monotonically increasing function, right? Then you look at the extreme cases. I think the claim is that maybe somewhere in the middle, there's like a combination. I'm throwing an example that's not going to work, like 0.5 for both of them. That would be just 1. Right? It would be 0.5. If P and R are both equal to 0.5, F1 score is 0.5. But just from the definition of harmonic mean, right? If we have two variables that are between 0 and 1, their harmonic mean cannot be extrapolating outside of that domain. So geometrically, if you think about it as well, you shouldn't expect it to be larger than 1. But I would be happy to be proven wrong. And I think the example that I show here for variables that are not coupled together, certainly there's cases where just because the numerator and denominator have the same range doesn't mean that the output of them is going to be, the fraction of them is going to be within 0. Yes, Manoj.
I mean, like for example, I know that we took this as an example, but for even this to happen, 1.5 over 0.5, either P or R has to be greater than 1, which isn't really possible, right?
In this case, yes, but you could consider like let me erase this and give you another one just for the sake of illustration. 0.15 divided by 0.05. Now that could work, right? For a P and R between 0 and 1, you could have potentially these values. Again, my claim is that you can't, because it's P and R both in the numerator and in the denominator. If you had independent variables, maybe, but in this case, you can't. Yes, Shima.
For the case that F score is more than 1, we just should find a region that 2 multiplied by P multiplied by R is greater than P plus R.
Yes.
And I think that this may be possible.
Okay.
Don't you think?
I'm not sure. I mean, I'm encouraging everyone to think about examples of P and R with where this equation would hold. Let's table this for now and come back to it. I appreciate the question though, because you've now instilled doubt in me as well. But I'm still pretty confident that the harmonic mean of two variables between 0 and 1 cannot extrapolate beyond these two. At least if I've written harmonic mean correctly. Okay, so let me ask a different question then. We've talked about true positives and false positives and true negatives. And based on those, we define the variable recall and precision. But all the while throughout our course, we've been talking about accuracy, right? What I want to show you now is that we can actually define accuracy in terms of the values here, in terms of true positive and false positives and all that. Now, how do we do that? Accuracy just means that the ratio of everything we've done correctly compared to everything we've done overall, right? So now you can see in the numerator, we have true positives and true negatives as everything we've done correctly, and then also summed with the false parts of our mistakes. And that is accuracy, right? So thinking about things in terms of the true positives and false positives not only helps us define these additional metrics like precision and recall in addition to accuracy, it not only helps us to consider cases where the errors of the mistakes we make might have different weighting, like the case of the medical example where we wanted to make sure that, false negatives don't happen and false positives, okay, probably less so. But there's also another case where false negatives and false positives are very important to Manavji's question, and that is class imbalance. So what does it mean to have class imbalance, by the way? Yes, Mujtaba.
When we have different number of samples in each class.
Right, so let's consider a data set. I have a data set of 9 positive circles, or nine circles of one class, and 1 plus of another class. And I give you a classifier that's a very excellent, very accurate classifier. What is my classifier? The classifier takes any input and gives a circle as the output. What is the accuracy of this classifier?
100%.
100%.
How much?
100%.
100%.
Well, it's not 100%, at least not on the training data set. I say the classifier, anything that goes in, it's going to predict as a circle. So what is the accuracy of it?
90%.
90%, right? We have 10 samples, one of them is a plus, so the accuracy is 90%. Now, what is the true positive rate? Or what is the true positive count here for this data set? It's 9. What is the false positive? It's 1. And what is the false negative? It's 0. Assuming that, okay, I guess I screwed up the plus and minus class, but bear with me. So when you put these numbers together, now you get a precision and recall, and then an F1 score that's not as glorious as the accuracy, right? And so especially for cases, Manavjit, where you have class imbalance, you should not be looking at accuracy, because accuracy is just going to be misleading. You could be completely ignoring one class, and looking at accuracy would just be silly. So there you have to look at false positive, etc. Now, just to maybe expand a bit your horizon of where true positives and false positives come in, we've always talked about, this two-dimensional grid of T and Y, but clearly this can also be expanded to the multi-class setting where you have different classes, and you might have, one class be misclassified as class 2 or misclassified as class 3 or class 4, etc. And so what happens there is then you have what's known as a confusion matrix. And what ideally you want is you want the diagonal of this confusion matrix to be very high values, because that means that the correct target and the prediction and the target are the same. You've done things correctly. And then everything on the off diagonals is mistakes. Right? Oh, I misclassified a 2 as an 8, or a 3 as a 5, or a 7 as a 1, whatever. Those are everything off diagonal. Now, I don't really know of methods that come to give, alpha, beta, gamma specifically for all the cells that exist on the off diagonal, so that's just a bit too hard. But if you want, you could, and you could bring that into the optimization for the multi-classes. Okay, now there was another question asked earlier on. Yes, Mustafa?
I want to note one thing. Will you please go back in your slide?
Okay, where should I go back to?
Yes, next. No, when we are talking about harmonic mean F1, so I have
the harmonic mean
confused a little.
Here.
Yes, yes. Okay, thank you.
No problem. So there was a question earlier on, maybe also from Mujtaba, who said, if I put my targets to be -1 and 1, then I select my threshold for linear classification to be 0. But maybe for some reason, based on class imbalance or whatever other reason that I have, 0 is not the best threshold, right? And I want to explore what the different values of the threshold might be in terms of the performance of the model. Now, based on all that we've learned here, we shouldn't only look at accuracy, but maybe we should look more closely at the precision recall itself. So we have something called the precision recall curve, right? Where on this axis we have recall, on this axis we have precision. And every single point on this chart over here is different values of the threshold that we can choose to do the classification for our model. And then ultimately what we'd like to see is the area under this curve to be maximal, to have maximal precision and maximal recall. So each point is a specific threshold used by the classification model to make binary predictions. Now, as one can imagine, we looked at the fundamental building blocks of mistakes, which were true positives and false negatives, etc. There are a ton of ways of combining these together. And so these are kind of the 4 that we looked at. But you can look at any combination depending on the domain of these and even more complex combinations like the false negative rate or the true negative rate or whatever rate that you want and optimize for that depending on the domain that you have. I want to remind again that metrics allow us to evaluate a model's performance on a data set that we care about, but we may not be able to directly optimize for those metrics or even formulate what we care about. And that's why we design loss functions, again, as a proxy for what we care about. Like in the case of last lecture, we had, this loss function here, which was even difficult to optimize because now we had a choice of hyperparameter built into it. Do I add more regularization? Do I add less regularization? What do I do? Right. So we just need to be aware of the difficulties in trying to first formulate what we actually care about, and then go about solving it. At each step, we're going to make some assumptions that could creep into, the performance of our model overall at the end. So any questions before we talk about the perceptron algorithm? Yes, Guru.
Is there any metric to determine whether a data set is balanced or imbalanced? Or is it just heuristic?
Is there a metric to determine the imbalance in a data set?
Yeah.
So I might not be correctly understanding the question, but you can probably just go through the data set and tabulate the number of samples that exist per class. And if one of them is outweighing the other by some factor that you think is too much, then that would be imbalance.
Right. So it is just that. I mean, I'm saying, is there a specific metric for that?
Oh, I'm not aware, but perhaps there is.
Okay.
But class imbalance is something that, up to a certain point is completely tolerable. In fact, the MNIST data set, which is, the very famous handwritten recognition data set, has 10 different classes, and I think like 50,000 or 60,000 training points. And when you go through it, it's not like every class has 6,000 samples. I think one of them even has like 4,000 something, 3,000 something. So there's one that's certainly off, but then there's others that have more, and on average, they balance out to be 6,000. But there's always a bit of class imbalance in your data. And we talked about like various noises that creep in. That's also another type of noise that creeps in. Not only attribute noise, not only label noise, not only data noise, whatever, but also class imbalance is another thing that throws it up. That's why before, and this is a good time to emphasize this again. Before even defining your model class or your objective function or attempting to optimize, or as many people like to do with the PyTorch, before doing like backprop, whatever on your data, actually look at the data, right? Because there's many questions that might guide your design choices, like class imbalance, like the domain or the range of the data that you have. If one of your algorithms is like the KNN that you're using and your scales are completely off, that's not helpful, right? So you need to have a good understanding of the data first before being able to model it.
Right.
There was another hand, Shima.
Yes, actually, I have two subjects to talk about,
Mhm.
if the time allows. About the imbalance class, I have a project about I have such project, and the recall and precision were the best measures
Mhm.
that we could use to determine the algorithm works well, not the best, but better than others. Like accuracy is not a good measure here, but recall is better, shows the strength of the method on imbalance class actually.
Mhm.
And about the F score, if I can talk about this after class, after recording, but what I have found an example.
Did you find an example, Shima?
Yes, actually.
Okay, well, share that example with us. Let's plug it in. I'm
Okay,
curious.
actually, the problem is from precision and recall.
Okay.
The precision is true positive on some of true positive and false negative, and this is not guaranteed to be between 0 and 1. Consider this example that we have 5 samples,
Mhm.
no matter which label they are. 5 examples, and we true positive is 3, and false negative is 2.
Okay.
And we have no false positive.
Okay.
Okay, so true positive will be more than false positive plus false negative.
Let me write this down. So you're saying we have n equals 5.
Yes, n equals 5. TP is 3.
False negative is 2, and false positive is 0. That's what you're saying.
Yes.
Okay. So in this case, then what is the recall is 3/5.
Precision. Oh, sorry. If true positive is okay. Actually, I want to say that I have a mistake in calculating something here, but I want to say that um, the denominator is more than okay. I more. This
Okay.
example.
So and feel free to also give other examples after class or on Discord. That's absolutely fine. I
Yeah.
think in this case, if my calculations are correct, the recall would be 0.6 and precision would be 1. And if we
Yes.
put that in, that's 2 times 0.6 times 1 divided by 1.6. That is smaller than 1.
Yeah,
Okay.
sorry.
So right, but good attempt though, Shima. Yes, Guru.
So instead of having precision and recall, can we just use F1 as a proxy for precision and recall? So Shima was talking about a project where she has precision and recall, which she has calculated for an unbalanced data set.
Yeah.
So instead of talking about those two, can I just talk about F1 score?
Yes. I mean, that's your choice to do that, or you can, if you have a threshold like we saw in this figure here, you might even want to look at neither of them and just the area under the curve of this curve that exists, right? Which, and all of these are, okay, the slide isn't showing. All of these are a proxy for F1 score too. So they are the building blocks that go into it. Ultimately, the fundamental building blocks are TP, FP, TN, and FN for binary cases, and the whole confusion matrix for multi-class cases. Yes,
Okay.
Manoj.
Like, just iterating back on the question about imbalanced dataset that Guru
Mhm.
asked.
Yeah.
Like we just saw in last couple of classes, while calculating entropy, right? The higher entropy would usually mean there are more equality between the two different samples, and if it is lower, then it would mean that one is very less and other is a lot. So that is why how we can easily, in those cases, we can just calculate the entropy to see which one, like how to make a decision between the two samples, right? So
Okay.
if we are calculating entropy, we would know like we can indirectly calculate entropy to see the imbalance in the data set, how balanced the data set is. So
That's a very good point. So the entropy of the empirical data that we have is one measure that you can use, and if it's very high, that means it's uniform across classes.
yes. I mean, like to get a base, like a first-hand understanding of the data set is imbalanced or not, or to what degree we can use that. So in that context, similarly, we can use Gini index as well, because they are on the same, like they measure kind of the same thing. So that's an thing.
And remember, the entropy for n variables is capped at what value?
N bits.
N bits, right? So you know that if you want perfect balance, you want something that's very close to n bits for your entropy. Okay, excellent questions, excellent discussion. In the time that we have left, let's talk about the perceptron algorithm.